seen about your two-cavity Klystron amplifier. Okay. Today we will go for Reflex Klystron Oscillator. So Reflex Klystron Oscillator. So it will generate the microwave frequency signal. Okay. So two-cavity Klystron amplifier amplifying the weak signal, and this Reflex Klystron Oscillator, it will generate the required microwave frequency signal. Okay. So if we are going for your Reflex Klystron, it is having some properties. The properties are, if you are seeing your Reflex Klystron Oscillator, here you will have low efficiency. It will have low power, single cavity and variable frequency. So in two cavity you are having buncher cavity and catcher cavity, and here you are having just one cavity, only one cavity you are having. Okay. And here you can go for variable frequency. So there is frequency range, say from 4 GHz to 200 GHz. You can generate any frequency signal from 4 GHz to 200 GHz. And efficiency is low. Say suppose if you are going for your theoretical efficiency, it will be around 22.78, and if there is the practical efficiency, it will be around 10 to 20%. Okay. So these are some of the drawbacks that you will see in case of the Reflex Klystron Oscillator. Now let us see the construction of your Reflex Klystron Oscillator. This is the construction of your Reflex Klystron Oscillator. Here you are having the cathode is there, focusing electrode. So by adjusting the focusing electrode, we can adjust the flow of electron. Here you are having just one single cavity. Single cavity means here we are getting the RF output signal. Here you are having the anode, and finally here you are having the repeller. Suppose if you are seeing here, you are having two different voltages. One you are having this anode voltage. One you are having anode voltage, and another one you are having the repeller voltage. If we are comparing the anode with respect to cathode, the anode is positive terminal, is positive with respect to your cathode. But on the other hand, if we are considering the repeller, repeller is negative with respect to your cathode. Okay. So suppose if you are seeing the flow of electron, the flow of electron will be from negative to positive always. Now what is happening? The electron, they are emitting from the cathode. They are moving towards the anode. As anode is positive, they will move from negative to positive. So they will reach here at the gap. They will reach here at the gap. And as the electrons are in motion, they will continue to be in motion. Okay. They will again move straight. But after moving certain distance, they will come to know that this repeller is negative. So as the repeller is negative, they will return back. Okay. So it depends upon the electron, what you are having the voltage here. If the electron reaches here, and during that time if you are having the more positive voltage, the electron will penetrate more in the repeller space. On the other hand, when the electron is reaching here, at that time the gap voltage is 0, it will penetrate moderate. On the other hand, when the electron is reached at the gap, and during that time if you are having the negative voltage, the penetration of electron in this repeller space will be less. Okay. And one thing is there, that electron will never reach to the repeller. It will never reach. Okay. So what they will do? As they are in motion, they will continue to be in motion, and when they will realize that yes, another one is negative, they will return back. So if you are seeing this electron when it reaches the gap, during that time, here you may have the positive voltage. As you are having the positive voltage, it will penetrate more. Okay. And it will return back. Okay. About this electron, here when the electron came, here the voltage was 0. Here as the voltage was 0, it will penetrate moderate. It will penetrate moderate. and similarly for this the voltage was negative, so its penetration will be less. If you are seeing this area is called your repeller space. So when all the electrons are returning back, these electrons can able to form a bunch. These electrons can able to form a bunch, and we can go for making the bunch provided that if we are adjusting the anode voltage and the repeller voltage. So if we are adjusting the anode and repeller voltage properly, then it is possible to make a bunch from these electrons. Okay, and as you are knowing the electron, they will possess the energy in the forward direction, and when they return back, here whatever the energy they will possess in the bunch, that energy they will deliver it at your RF output. So energy they are delivering here at the RF output. Okay, so this process will continue. So first you are having one bunch, then second bunch, then third bunch, like this. The different bunches will be there, and this to and fro motion, this will result in the oscillation, and that will result in the required frequency signal. Okay, and in order to have the sustainable oscillation, we need to adjust this anode voltage and repeller voltage. Generally, the anode voltage is kept around say 250 to 300 volts DC. Okay, we are keeping the anode voltage from 250 to 300 volts DC, and we will adjust the repeller voltage. Okay, so we are keep this anode voltage some fixed, and then we will adjust this repeller voltage so as to get the proper oscillation. This is the your construction and operation. Next we will go for the Applegate diagram of your reflex Klystron oscillator. So your Applegate diagram means what is happening here, that we will see in that one. Okay. Diagram of your reflex Klystron oscillator. So Applegate diagram will be applicable here from gap to start until what is the activity you are having in the repeller space, that only will be there. So this is the Applegate diagram. Here it is telling the voltage at gap. At gap, what voltage you are having. Okay. So here let us assume that you are having one early electron. E and the base is small. This is the early electron. When the early electron reaches the gap, at that time the voltage was positive. Okay, positive. And then you are having this electron. This is your reference electron. When the reference electron reaches at your gap, during that time the voltage was 0. And third one, this is your late electron. So this late electron, when it reaches the gap, during that time the voltage at the gap was totally negative. Okay, so you will have many more these early electrons, you will have many more these late electrons, and overall early and late electron will be cancelled out. Okay, and here you have the reference electron. So reference electron means the voltage at your gap will be 0. Now all these early electrons, all these late electrons, and the reference electron combinedly they will make a bunch here. Okay, so first let us assume you are having the reference electron. So when the reference electron reaches at the gap, during that time the voltage was 0. So this is the position. It will move towards the repeller. This is the repeller and this is the repeller space. This is the repeller space. Repeller space means this one. So reference electron, it is moving towards the repeller, and in the repeller space it is just returning back. On the other hand, you are having this early electron. Early electron, when it reaches that gap, during that time the voltage was positive. So as the voltage was positive, it will penetrate more in your repeller space. It will penetrate more. state point. So these two are forming the bunch. Similarly, you are having the late electron. Late electron, when it is reaching at the gap, the detected the voltage was negative. As the voltage was negative, it will move towards the repeller, but it will cover less distance as compared to your reference and your early electron, and again it will also return back. So all these, your early electron, reference electron and late electron, they will form electron bunch. Electron bunch means they are producing the energy and they will return the gap. Here they will return that energy, and from your RF output the signal can be taken. Okay. Now if you are seeing this, so you are having the bunching limit. Bunching limit is starting from this to this point. This is your bunching limit. Here only you will have the bunch. So whatever the electrons you are having with the positive, negative and zero, combinedly they will form the bunch, and you will have the bunch, one bunch per cycle. So from here to here you are having bunching limit. Again you will have another bunch. Another bunch will start from here to here. From here to here you will have the another bunch. So here also you are having early electron, reference electron, and this is the late electron. They are also going to make another bunch. Okay. Now if we are seeing that where you are having this formation of bunch, okay, from here we are considering. So from here we are considering you are having one negative point, one positive point. Total it is making one cycle, and then you are having negative going and half of the positive going. So this duration from your reference electron to where you are having this bunch, this is called your transist time. This is called your transist time, or we can say that the time taken by the electron to move from gap towards the repeller and back to gap, that is called the transist time. Moving towards the repeller, returning back. So total what is the time? That is your transist time. They are called optimum transist time. Optimum transist time means when say how we should address this whatever the electrons they are moving towards the repeller and returning back, and formation of bunch is there, how we can go for the sustainable oscillation. So that is your optimum transist time, and your optimum transist time will be equal to your n plus 3/4. This is your optimum transist time. So optimum transist time is your T is equal to n plus 3/4. Here if you are seeing this transist time, so here one negative going, one positive going, one cycle completed. This is one negative going and this much positive going. So if I am seeing this transist time, this is your one. So this is also one optimum transist time. Okay. So here n is integer, means we can say that your 1 3/4, 2 3/4, 3 3/4, all these are your optimum transist time. Optimum transist time means if we are adjusting this as a transist time, you will have sustained oscillation. So you will have the continuous oscillation. Okay, undamped oscillation. So continuous oscillation will be there. So for that we have to adjust the transist time. And how you can adjust the transist time? You can adjust the transist time by adjusting your these anode and repeller voltages. Okay. Characteristics of your reflex klystron oscillator. Here you are having the frequency range of 4 GHz to 200 GHz. So 4 GHz to 200 GHz is the frequency range. So suppose if you are going for the output power you are having 1 milliwatt to 2.5 watt. You are having the theoretical efficiency. Theoretical efficiency is 22.78 of 10 to 20%. Okay, and tuning range. If you are looking for the tuning range, you can get the say 5 gigahertz frequency at your 2 watts, and you will get say 30 gigahertz at your 10 milliwatts. Construction, operation, Applegate diagram, and we have seen the performance characteristics also. Then you are having the applications. So what are the different applications of your Reflex Klystron Oscillator? So some of the applications are, we can use your Reflex Klystron Oscillator as signal source, as in case of your microwave generator. We can use it as local oscillator in microwave receiver. We can use it as FM oscillator in microwave links, and we can use it in parametric amplifier as pump source. Now my question is, what is this local